All right, we're going to talk about two-dimensional motion. We talked about one-dimensional motion when we were throwing something up in the air and then bringing it back down if you were standing in the same spot. But things get more interesting and more exciting, I think, personally, when we're throwing things in two dimensions. For example, if we're going to throw a baseball, and here's my weak attempt at a baseball, there it is, and we want to throw it to somebody at home plate, maybe to throw them out. What happens is we throw the ball and we give it some initial velocity, and it has a parabolic path, and hopefully by the time it gets this far, you've given it enough initial velocity and the right angle, and then what happens is it ends up getting the player out at home plate. Okay, well, that's great. And so this line right here, this parabolic arch that I drew right here, is the path of the ball. And what I like to do is say at time t equals 1, from the origin, let's say that this person threw the ball 3 feet up in the air, right? So this is the origin. And I'd like to draw this in standard position. Well, actually, I should put the origin through the baseball. Let's do that. Right? And they were 3 feet up. This would be at 3, okay? So the path of the ball, I could say at time t equals 1 second, 2 seconds, 3 seconds, 4 seconds. All the way down here, I could describe the path of the ball using a vector, a position vector, pointing at where it is at some certain time t. And then I could say that the position is going to be x of t and then some y of, whoops, that's a y of t. Describing, right? So I could say its position is a set of parametric equations, and I could actually write, I could write it as a vector x of t, y of t, and then write it as a set of parametric equations, x of t, y of t, and have two sets different equations to model the behavior. Well, how do we figure out what these distances are that the ball has gone in the x direction and in the y direction? Well, I'd like to start, if it's at all possible, with what happens when we throw the ball. Well, we gave it some initial velocity. All right. We gave the ball an initial velocity or an original velocity. And the velocity has a magnitude. And then we threw it at an angle with respect to the horizontal. And you can't really see that angle here. With respect to the horizontal, I threw it with an angle, theta, with respect to the horizontal. So I'm going to be given an original velocity and a theta, its direction angle. So I could come up with a velocity vector, which would be the original velocity, the magnitude of it, times the cosine of theta, times the y component of the velocity would be the original velocity's magnitude times the sine of theta. And that would give us the velocity vector. And we could say that this is the velocity component in the x direction. I'm having trouble writing today. And then this is the velocity component in the y direction, couldn't we? And so let's harken back to Algebra 1 when we were trying to figure out how we calculated distance. Well, distance was nothing more than rate times time. So I can say that the ball went in the x direction, its rate times its time. Well, it went its rate, which would be here, maybe feet per second, times time. So I could say that this is the velocity in the x direction times time, which equals the magnitude of your original velocity times the cosine of your angle, theta, times t. Now, this is the coefficient, right? The t does not go in with the theta. And so this would be in feet per second, and this would be in seconds. And feet per second, if we think of the units, feet per second times seconds gives you feet if we did a dimensional analysis, because the seconds would cancel. Well, what about the y? Well, it would certainly be the velocity component in the y direction times t, which would minus, well, we have some gravitational forces acting on this, and so it would be minus 1/2 gt squared plus my original height. So let's write that with the magnitude velocity. The magnitude of velocity times the sine of theta, which is its coefficient, times t, minus 1/2 gt squared, where g is the acceleration due to gravity, depending upon what planet you're on, plus your y original. Okay, so let's see if the units work out. This would be feet per second times seconds, which gives you feet. This here would be, the gravitational constant is always feet per second squared. So this would be 1/2, well, feet per second squared times seconds squared, which gives you feet. And your original height would be in feet. So then you would be able to describe your y height in terms of your rate times your time, the component part of the velocities, plus or subtracting the gravitational constant influence, and your original height. Okay, so let me summarize that really quickly here. X of t is going to be equal to the magnitude of your original velocity times the cosine of the angle that you threw your ball times t. Y of t is going to be equal to the magnitude of your velocity times the sine of your angle that you threw the ball at times t minus, let's say we're in feet per second, it would be 16t squared plus whatever original height you were at. So these would be for projectile motion. And they're parametric equations. Okay, because throwing a ball is a perfect way to describe, parametric equations is a nice way to describe motion, and throwing a ball is certainly motion. All right, let's do an example. I have, this is from the book, it's from example number 9. Let's say Kevin is hitting a baseball 3 feet above the ground with an initial speed of 1 foot per second at an angle of 18 with the horizontal. Will the ball clear a 20-foot wall that's 400 feet away? I'm going to cover these answers up, okay? All right, so we want to know, first of all, what the parametric equations are for Kevin hitting the ball. So let's set that up. Well, we know x of t is going to equal the initial speed. Now, speed is a magnitude, so this is going to be 150 times the cosine of 18 degrees. Now, remember, that's a coefficient times t. And the y component of the position is going to be 150 times the sine of 18 degrees times t, another coefficient here, minus, now we're in feet per second, so that's going to be negative 16t squared plus 3, because that's how high we are that's how high the ball was when it first initially was struck by the bat. All right, so what we're going to do is figure out how many seconds after the ball is hit does it hit the wall. Okay, well, let's see. In our picture, in our mind, when we're hitting a ball, here's the ball, and I'm like this, I want to know how far away, first of all, is the wall. Well, the wall is here. The wall is 400 feet away. Now that's 400 feet in a horizontal direction, isn't it? Why, yes, it's in the horizontal direction. So if I want to know how many seconds it takes to get there 400 feet horizontally, this is my horizontal component, so I'm going to set the horizontal component equal to 400 feet. Okay. All right, so let's do that. We'll say that I want to know when x of t is equal to 400, which means 150 cosine of 18 degrees. Remembering that's a coefficient, t equals 400. So t equals 400 over 150 cosine of 18 degrees. All right, now let's pull out the calculator. And I'm going to go, let's see, I am in radians, so I need to change that to degrees because I was given degrees. Now I'm going to say 400 divided by 150 cosine of 18 degrees. And that's going to give me a number. What is that number? That's 2.803899. But what I'm going to do is store that. So store that in alpha A. So I've stored it in A. So that's how many seconds it's going to take once it leaves the bat to go 400 feet. Does everybody understand that we set the horizontal distance equal to the x component because that is the horizontal distance? So part A says how many seconds is it going to take to get to the wall? Well, it's 2.8 roughly seconds to get to the wall. Then it says how high up the wall does the ball hit? Well, what does that mean? That means I want to know how tall it is when it's at the wall. Well, how do I figure that out? Well, I need to know what this function's value is at this value of t. So I want y of 2.80399, right? And I'm going to hit approximately here. And I can say then, using this equation, 50 times the sine of 150 times the sine of 18 times alpha A, right? Because that's what I stored this in, minus 16 alpha A squared plus 3. And that tells us we're at a 7.178 feet up. So does it clear the wall? Well, the answer is no. So that's how high it hits the ball, how high it is when it hits the wall. So does that mean does he clear the wall? So it's not a home run. Does not clear the wall. At 400 feet. Since, how did we know? Since 7.178 feet is less than the wall is 20 feet high. All right, now part C says, explain why Kevin's hit might be caught by an outfielder. Explain why his hit would likely not be caught by an outfielder if the ball had been at a 20-degree angle. Okay, well, so what's interesting about this is, do you think that the outfielder could jump? If they, let's say they were 7 feet tall, could they jump a foot up to catch that? Sure, they could catch that. But now the part C is, so we're going to say at 7.718 feet up, an outfielder could catch that. That ball. Well, now I'm not sure I could, but I'm 5'5", so maybe I would have had trouble catching that ball. But it's, anybody that's a little taller than me, more athletic, obviously would have been able to catch it. But now they're giving us another twist to the story and saying that it's 20 degrees. Well, 20 degrees. Well, what do I have to change? I have to change these two equations. Okay, so that means my angle is now not 18, but now let's say it's 20. So I'm going to change my parametric equations, and I'm going to say x of t is equal to 150 times the cosine of 20 degrees times t, and then y of t is equal to 150 times the sine of 20 degrees times t minus 16t squared, and we're still 3 feet up in the air. So how do I find out where it is, or how long it takes it to go 400? Because that would be for the first step. I would say x of t equals, helps if I write it right, x of t equals 400, because that's the horizontal distance. And I would say 150 times the cosine of 20 degrees equal t. T equals 400, so t equals 400 over 150 times the cosine of 20 degrees. So let's do that. I can actually go up here and grab this and then change the degrees to 20 and press enter. And that's going to be approximately 2.8378. And I'm going to store that now in alpha B. And then how high is the ball going to be? Well, I want y of 2.8378. So what does that mean? I'm going to take this equation up here, and where I see 18, I'm going to put 20. And where I see alpha A, I'm going to put alpha B. And I get 19.773, I guess if I round up 8, right? Feet. Now, Superman might be able to catch that ball, but I don't think a regularly sized human could catch a ball at the almost 20-foot mark. But still, does it clear the wall? The answer is no. No, it doesn't clear the wall. All right, so now I've done this problem all algebraically. Okay, what if I were to ask some questions, some interesting questions? Well, for example, how high, what is the maximum height of a ball? Well, how would I find the maximum height? Well, what component is being described here? It's the y component. So I'd find the maximum of this function, and that would tell me how high the ball went. Now I could go to function mode and figure that out. So let me get another piece of paper here. So if I want to know, I'm making a part D here, the max height of the ball. Okay, and let's say I want to know what the max height of the ball is. Well, we're going to assume that we're in our original equation, which was 150 times the cosine of 18 degrees. Remember, that's coefficient times t, and y of t is equal to 150 times the sine of 18 degrees times t minus 16t squared, and we said it was 3 up. Okay, so if I wanted to find the maximum height, what's the maximum height? Well, on the path, the maximum height is the y. So I'm going to set this in my calculator. So I'm going to go into y equals and go parentheses 150 times the sine of 18 degrees, close parentheses, times x minus 16 x squared plus 3. And then let's, I'm going to have to change the window, I'm sure. Whoops. So let's go to the window. Whoop, escape, so I can quit. Let's go to the window. And my x min, or my y min, I'm going to just make it -2 so I can see the axes. Now, I'm 3 feet up. I don't know. I'm going to make, oh, I know how long it's in the air, don't I? They said it was in the air for 2.8 seconds, right? So I can make this 5 maybe. And then my y min, now remember, now x min is t, is time. And y min now is the height. So I'm going to make this -2 so I can see the x and y axis. And then I'm going to make the max height, I don't know, 100, just to see if we can see it. All right, and let's see if we can see it on the graph here. I was worried only for a moment when it didn't show up there. Okay, so how do I find the max? You go second calculate, whoop, not gold calculate. Second, calculate the maximum, and I need to be on the left side. I'm on the left side, and I need to be on the right side. And then I want my calculator to guess. And so the max occurs when t is, what is that, 1.44, can everybody see that? 1.4485, a comma, and this is 36.57. Now note, this is t and this is y of t, right? Because that's what we did in our calculator. Now I'm going to go second quit, and I'm going to store x, because that's the time that it happened, into alpha c. So that I remember that, okay? So that's the time, and this is the max height. Okay. The other interesting question would be, well, when does the ball hit the ground? So let's see, when does the ball hit the ground? That's E, that'll be our next question. When does the ball hit the ground? Well, when does the ball hit the ground? Well, that's when its height is 0. So we would set y of t equal to 0. So that would be 150 sine of 18 degrees times t minus 16t squared plus 3 equals 0. All right, and let's do that on our screen. We're going to go to graph. And how do we find the 0 on a graph? Well, we hit, I did it again. Second, calculate the 0, which is number 2. And I'm going to be on the left bound here. And the right bound. You want him to guess? Yes, the answer is, what is that? 2.96, comma, 0. Remembering that this is time and this is y of t. Okay. And I'm going to store that when I go back, second quit. I'm going to store that into D. Whoops. Alpha D is right here. Okay, there we go. So I stored that into D. Now you might say, do I have to store all those numbers? Well, the answer is no. No, you don't have to store all those numbers. But the reason is that I'm going to show you now how to graph this on your calculator in parametric mode. Okay, so we're going to change the mode on our calculator. Okay, and right now we're in function mode, and we're going to hop over to parametric, second quit, and then we're going to go to y equals. And you'll notice in parametric mode, just like we've done before, you get x1 of t, y1 of t. So obviously we're going to put the horizontal component into x and the vertical component into y. So let's do that. We type that in, we get 150 cosine of 18 x. Now when I type in, t, when I type in t in parametric mode, I get it, or x, I get a t, which is nice. All right, then we're going to say 150 times the sine of 18 degrees times t minus 16 t squared plus 3. So now I have my horizontal component, my vertical component in parametric mode into the graphing part of my calculator, and then we're going to go to the window just to see what looks different about it. All right, well, what looks different about it? Well, I have a t min and a t max. And I always leave the t step alone. And I have an x min and an x max. Now, x means how far am I going to go horizontally? Well, do we know how far we're going to go horizontally? Well, no, we're going to go at least 400. So I'm going to make x max 500. And then y max, that's how high we're going to be. And we already figured out that the high is going to be about 36. So I'm going to make this, instead of 100, let's make that, I don't know, 50. Okay? Now, I know that it's only going to take, we figured out how long? 2.8 seconds. Okay? to get to the wall. So I'm just going to put 4 here and see what happens. All right, now I'm going to go back to y equals, and I remember the last time we spoke about parametrics, we could hop over to this side over here using the cursor, the right arrow or the left arrow, and we could toggle this to, well, blue is fine, but we could use the what I like to call follow the bouncing ball that leaves a path, and then we can press OK, and then we can look at our graph. Let's see what happens. Well, there it is. We just saw the ball fly through the air, which is pretty cool. Now, what's interesting is that we found out when it was at its maximum, didn't we? We did. We found out it was at 1.4485. Now, I did this in function mode to find out what the actual value was, but I stored the time that it was going to be in function mode at its maximum in C. So I can now use the second calculate button, and you notice that it looks a little bit different, that when you hit the second trace or calculate when you're in parametric mode, what comes up is value. So let's do, then these other 3 are for calculus. So let's press value, and I want the value of my, where I am at t equals something. Well, let's find out where we are at t equals c. Okay, so I'm going to go alpha c, right? Because that's where I stuck the time. Well, let's see what the calculator says. The calculator says at 1.44857, which is what we said this was, we are at a position of 206.6433. That's where I am standing in the x direction. What is that? 204.64. And then how high am I? Well, I am at that 36.57, which is what we thought we would be at. Now, at this time, I didn't calculate how far I was horizontally, but parametric mode tells me where I am horizontally and where I am vertically. It's like the vector is pointing directly to my location. All right, what about when I'm on the ground? Where did I store that? I stored that in D. So let's go second calculate the value of my function when t is alpha d. And look at that, I'm on the ground. And where am I on the ground? At 422.32. I'm on the ground at, this distance here on the ground is 422.32. And then I'm on the ground, right? Because this is 3 up here. Well, that tells me that I have to go, the ball is going to plow through the wall and hit the ground, right? Because the wall is standing at 400, right? Now we wanted to know where the ball was, how high the ball was at 400. Did we solve that? We did. We found out that the ball at 400 will be at 400 feet horizontally when time was equal to this. And I do believe I stored that in alpha A. Let's see. Second, calculate the value of my parametrics when I'm at alpha A in time. Well, there you go. You're at 400 feet at time 2.803899, which is what we said. And how far high up the wall are we? We are at 7.178. Very cool, right? So you can find out where you are in space using parametric equations that act like position vectors that point to where you are using a horizontal component and a vertical component. Now, wouldn't it be nice if we could actually get the wall on this graph? Because that's kind of fun, right? To put the wall on, well, that would require another set of parametric equations, right? So let's put the wall on here. See how we get the wall. Well, we need the wall to be standing where horizontally? Well, we need the wall to be at 400. It's going to be standing for all time at 400. And we need it to be 20 high. 20 feet high at 2.803 seconds, right? So I'm going to say I want, I need the wall to be 20 feet high when t is 2.803899 seconds. And so I need to know, that's t. And if I divide, or if I go 20 divided by this, right, wouldn't that be how tall I want the wall to be? Let's see. Let's try it. All right. Let's put 400 because we want 400 here. And I want it to be a growing wall, right? So I want it to be 20 divided by 2.803, I think, times t. I think that's what I want to do. We'll try it out and see what happens. Okay, and I want to go up here and follow. I don't necessarily have to follow the bouncing ball on this one. And let's change the window to, let's make our T max when we're going to be at the wall, right? When are we going to be at the wall? We said we're going to be at the wall at 400 divided by parentheses 150 times the cosine of 18 degrees. Now I know that this is a lot to follow, but see, that gave me the nice number there. Okay, now let's see what happens when we decide to graph it. Oh, well, that didn't necessarily get us there, right? I need them to be drawing it at the same time. So I have to go to my mode, and I'm going to go down to where it says sequential, because if it's in sequential mode, that means it's going to graph y1 first, and then it's going to graph y2. But I would like them to graph them at the same exact time. So I'm going to put simultaneously, go second quit, and then graph. And you see the wall's rising out of the ground, but you can see that the ball is not going to hit or go over it. Okay, now you'll notice that I have some space between the ball and the wall here. If you can't see it very well, but there's a very little bit of space here. And that's because my window here, my t-step is 0.138. So if I made my t-step smaller, like 0.001, let's see if it gets closer. Okay, well, you can see right away that 0.001 is probably too small. So I'm going to press the on button. And why is it too small? Because it's going to take it way too long to do that. Let's try 0.01. I might be sorry I did that too, but now that's a little bit more reasonable. So this video is not 3 hours long for it to get to the wall. Okay, so what have I done? I've created a wall with the slope of 20 over well, it's graphing 2.80399 times t. And we'll see if it hits it. Boom, it hits it. You see it? And it's going to bounce off and somebody can grab it. It's pretty cool, I think. So what did we find? I found the slope. What is this going to be? This is going to be how high the wall is over seconds. So it'll be feet over seconds, means that the wall is going to be, you know, that my three little piggies are going to build the wall from ground zero to 20 feet high in this amount of time. And you'll see that it doesn't reach the wall, or it doesn't go over the wall for a home run. All right, that's a lot of words. I also took the liberty of showing you how, I wanted to show you how to do this on Desmos because we have this amazing technology at our fingertips. And so what I did was, when you're graphing parametrically on Desmos, what you do is you type in an XY point, which looks like a vector, right? So the X component right here, I have before the comma. This is 150 cosine of 18 times t. And when I do that, what pops up is, as you might remember, is slider. And yes, we want t to have a slider, And then I go comma, and then I stuck the y component. If you see over here, I put 150 times sine of 18t minus 16t squared plus 3, and closed it off just like it was a vector. Okay? And then I changed, because of our calculations, I changed the time to go from 0 to 400 over, you'll notice, cosine of 400 over 150 times the cosine of 18, because I knew that's when it was going to hit the wall. And then Desmos is a little bit more friendly because it'll let you graph a wall at 400 that's only 20 feet high. So I was able to do that, restricting the y, which is pretty cool. All right, so here we go. We're gonna go backwards in time, and then boom, he hits the wall. It hits the ball, and it hits the wall and bounces back. Well, it doesn't really bounce back, but what's pretty cool is that you're actually seeing the parameterized path, and I set it up like a vector because this is a position vector that points to where the ball is at time t equals whatever time you're at, which is really, really cool. And I'll put a link of this onto Moodle so that you can see it. And I'm going to save this. Okay? I'm going to pause this real quick. Now, when you want to see if it's 20 degrees, will it hit the wall? What are the two things we had to change? Well, I'm going to copy this line up here. Maybe. I'm not as good as my drivers are. There we go. Control C. Hop down here. Control V. And now I'm going to change this to 20. And I'm going to change this to 20. That's the only thing that's different, right? And the t still applies because t is still there. And now I'm going to hit, I'm going to go back to time equals 0. And let's see what happens to the wall and the balls as they. So the 20 degrees, you can see that, yes, the purple one hits the wall but doesn't go over it. So we could conjecture, right, couldn't we, as to what might cause it to go over the wall. Well, it's going to have to be something greater than 20, and we could figure that out. But I don't want this video to be too incredibly long, so like I said, I'll save this and post this link so you have it to play around with. All right, so let's do one more example. And the example is actually one from your homework, and it's about hitting golf balls. We might have some golfers. And this is number 50. Let me get my IPVO up. There it is. Nancy hits golf balls off a practice tee, which means from a practice tee, yeah, we're going to assume that's the ground. It's negligible. Unless, her tee is, a little bit off the ground, but we're not going to go there. Okay, so Nancy hits golf balls off the practice tee with an initial velocity of 180 feet per second with 4 different clubs. How far down the fairway does the ball hit the ground if the club making the specified angle off the club, making the specified angle with the horizontal? So I'm just going to do one of them for you so that you can set up all the rest, okay? All right, so the first one is 15. Now remember, she's hitting a ball with her golf club, and it's going to go all the way over, and it's going to hit the ground somewhere, right? This is the ground, and it's starting on the ground, ending on the ground. So we need to set up a set of parametric equations that will be our position vector in space, right? X of t horizontally and y of t horizontally. And my t looks a little weird. Sorry about that. All right. So for part A, my parametric equations are going to be x of t and y of t. So let's do that. Well, I'm going to take the magnitude of the velocity, which they're telling us right here, times the cosine of the angle. So it's going to be 180 times the cosine of 15 degrees times t. And that's going to be the horizontal distance. It's rate times its time. The vertical distance, however, has not only this velocity component, which would be 180 times the sine of 15 degrees t, minus, now it's got the acceleration due to gravity pulling down on it. So it's going to be 4 feet per second. So that's 16t squared. Now, my original height we said was 0. So I'm not going to add a 0. So that's my parametric equations. Now I want to know, first of all, it says, how far down the fairway does the ball hit the ground? Okay, well, I want to know what its horizontal distance is when it's on the ground. Well, what is on the ground? Well, remember, we have a maximum height that the y does, and then on the ground, the y is equal to 0. So that's my first step, is to set y of t equal to 0, and that's going to be 180 sine of 15 degrees times t minus 16t squared equals 0. Now, t I can factor out because this is just a coefficient, times 180 sine of 15 degrees minus 16t equals 0. So I can say that negative 16t I'm sorry, 180, I'm solving it in my head, I'm sorry, forgive me, equals 0. So we get 16t equals 180 sine of 15, because I'm moving this over. So t equals, did I do that right? Yeah, I think so. All right, 180 divided by, or sine of 15 degrees over 16. I just had a mental moment there. All right, so what are we going to do on our calculator? So I can quit. I'm going to do alpha y equals, gives me the fraction 180 times the sine of 15 degrees divided by 16 gives me 2.911. That's approximately 2.9117. That's when it's on the ground. So I'm going to stow that in alpha A. And then now I want to know how far down the fairway I am. So I want to know x of 2.9117, but I don't have to approximate because I'm going to use the stored value for this. So what am I going to say? 180 times the cosine of 15 degrees times alpha A, right? Because that's where I stored it. So she hit the ball 506 and a quarter feet down the fairway. So how do we solve this problem? What do? We set the y equal to 0 to find out when it's on the ground. Well, it's on the ground at t equals 0 because that's where we started. And you set the second component equal to 0 and solve for t. And then once you know how long it takes to get on the ground, then you can find out how far it went, because then you know how long it was in the air. Okay? So that's what I have for you today for parametric motion. So have some fun with that, and we'll talk to you next time.